All right. Hello and welcome. Today we're jumping into a really classic question, one that's basically the foundation for all of integral calculus. It's called the area problem. And yeah, it sounds simple, but trust me, the solution is seriously powerful.
Think about it for a second. We've got easy formulas for squares, circles, triangles, right? But what about the area under a curve? Like, say, a parabola? Your basic geometry toolkit, well, it just doesn't have an answer for that. So how in the world do we solve it?
The core idea here isn't brand new. The ancient Greeks, for example, had this brilliant method where they would try to fill up or exhaust a curvy shape using polygons, shapes they could measure. It was a fantastic start, but honestly a little complicated.
So the modern approach, the one we're going to use, makes this idea even simpler. We're going to use the most basic shape you can think of, the rectangle. And as you can probably guess, we're going to use a lot of them to get a pretty good estimate of the area.
Okay, let's break down exactly how this whole thing works. We all know area of a rectangle is just height times width. Easy enough. For us, the height of each little rectangle is going to be decided by the value of our function, f of x, at a certain point. The width is just a small, even slice of our interval, which we call delta x. And the last step, you guessed it, we just find the area of every single one of those skinny rectangles and add them all up.
Now this whole process actually has a fancy name. It's called the Riemann sum. Let's look at the notation here for a sec. That big Greek letter sigma, that just means sum up, whatever comes next. And what are we summing up? Well, it's the area of each rectangle. The height, f of x, times the width, delta x. It's the exact same idea we just walked through, just packed into one neat little formula.
The theory is great and all, but seeing it in action is so much better. Okay, let's dive into this with a real example. We're going to start by using what's called the right endpoint method.
So here's our mission, should you choose to accept it. We need to estimate the area underneath the parabola f of x equals x squared, starting at x equals 0 and ending at x equals 2. And we're going to do it using just 4 rectangles.
We can knock this out with a really clear, 3-step game plan. First, we'll figure out how wide each of our 4 rectangles has to be. Second, we'll find the specific x values that are going to set the height for each one. And then finally, we'll just add it all up and get our estimated area.
Okay, step 1, the width. Our total interval is from 0 to 2, so its length is 2. We need to cram 4 rectangles in there. So we just do 2 divided by 4, and that gives us a width, our delta x, of 0.5 for every single rectangle. Simple as that.
Now for step 2. Since we're using the right endpoint method, the height of each rectangle is going to be set by the function's value at the right edge of its base. So for our 4 rectangles, the right edges are at 0.5, 1.0, 1.5, and the last one at 2.0.
And here's where we put it all together. The total area is going to be roughly the width, 0.5, multiplied by the sum of all the heights. And the heights? We just get those by plugging each of our right endpoints into our function, x squared.
Okay, now we just have to crunch the numbers. We plug in our endpoints, so that's 0.5 squared, plus 1 squared, plus 1.5 squared, plus 2 squared. We add all that up and multiply it by our width of 0.5, and that gives us a final estimated area of 3.75.
So we have an answer, 3.75. But how good of an answer is it? Is that an overestimate, an underestimate? Well, to figure that out, let's compare it to a slightly different method.
So what happens if, instead of using the right side of each rectangle for the height, we use the left side? The process is exactly the same, but look at that crucial difference in the x values we use. For the left endpoint method, our points shift over. We're now using 0, 0.5, 1.0, and 1.5.
And would you look at the difference that one little change makes? Our right endpoint method gave us 3.75, but the left endpoint method, with the same function and the same number of rectangles, gives us a way smaller answer, 1.75. That is a massive difference.
So here's the key takeaway. For a function that's increasing like x squared is, using the right endpoint is always going to make rectangles that stick out over the curve. That gives you an overestimate. And using the left endpoint will make rectangles that sit just underneath the curve, which gives you an underestimate. And this visual just makes it crystal clear, doesn't it? Our left approximation of 1.75 is way too low. Our right approximation of 3.75 is way too high. The true exact area, which happens to be about 2.67 for this problem, is trapped right there in the middle, between our two estimates.
So,
This all leads us to the most important question, really. We've got an overestimate and an underestimate. So how do we close that gap? How do we go from a rough guess to a perfect, exact answer?
Well, the solution is actually pretty simple in concept. We just use more rectangles. I mean, if 4 gives us that big of an error, imagine using 40 or 400. As we pack more and more rectangles in there, they get skinnier and skinnier, and that gap between our high and low estimates just shrinks, getting us closer and closer to that true area.
And that brings us to the final, really mind-bending idea that just blows the door open to the rest of calculus. What would happen if we could use not just a whole bunch of rectangles, but an infinite number of them? What does that even look like? That right there is the question that the definite integral was invented to answer. Thanks so much for watching.